Jackson Hole. And as per Brent, I'd like to welcome you very heartily to this program, which is part of the Science Nature Tuesdays program at the Teton County Library. It's a partnership between geologists at Jackson Hole, the Bird and Nature Club, Teton Plants, and of course the library, without whom we definitely would not have been able to provide program actually at the library, which is certainly something we hope to get back to at whatever point that might be when the pandemic is waned enough. I might also mention that as many of you, most of you, maybe all of you know, Old Bill's fund raising program is underway, and I'd like to just ask you to think about the library through the Library Foundation and these three organizations that make up the Tuesday night Science Nature programs. If you were watching the slideshow before we began talking, you'll have noted then that beyond tonight's program, there's a very interesting program scheduled for Tuesday, October 6th, another Zoom program. It will be a combination of geology and adventure presented by Mike Adler. I think that'd be something you'd find very, very interesting. Again, as Brent said, questions, pose them via the chat option throughout the program as they occur to you as Simone presents. And I'll just make one editorial comment, and that is that I suspect most people don't really realize the critical importance of ores, and usually it's metals that come from the ores, that are truly critical for the existence of our modern 7+ billion person, technologically driven global society. So what Simone is going to talk about tonight is something that most people don't realize the importance of, but I'll encourage you to think about that as she presents. So let me go ahead and introduce Simone now. Simone is at the University of Wyoming in the Geoscience Department, Geology and Geophysics. She has a bachelor's from Illinois, a master's and PhD from the University of Arizona. She did postdoc research work at Carnegie Geophysical Laboratories. Her research statement says that her focus is in economic geology, and it's the study of hydrothermal systems, the fluids that transport through these systems, transporting metals, really, really important. She's interested in a wide variety of ore deposits. She has broader interests as well that include geochemistry, igneous petrology, mineralogy, and planetary geology. With respect to teaching, she teaches and enjoys discussing economic geology. She's particularly dedicated to undergraduate instruction and building the foundation for scientists of the future, and focuses on development of the students' critical thinking skills, which is something that too many people in our country seem to lack these days. So without further ado then, I'm going to ask you to join me in welcoming Simone Runyon. Simone, it's all yours.
Thank you so much. And let me share my my little slideshow for everybody today. All right, so hopefully that's nice and visible. Thanks so much, John, for the kind introduction. Thanks to everyone for being here. Thanks for the invitation to talk. Obviously, I'd rather be up in Jackson, but this is a great substitute given the circumstances. And John kind of hit on this already. So I consider myself an economic geologist, which, even though things like oil and gas are commonly economic, really focuses on the study of metals and metal-bearing ores. And so what I thought would be kind of fun today would be to just touch on a handful, 3 different systems across Wyoming. We won't be able to get into the gory details at all. It's just going to be sort of a flyby of each one of them. But to give you a very brief introduction to the crazy variety of ore systems that are present in Wyoming. And before we get into all of that, I do kind of want to step on my soapbox since I have one here. And John also kindly hit on this already. It's sort of why we study ore deposits still, right? We have to think very critically about what each and every one of us uses in our everyday lives and sort of where all of those raw materials come from. So this is what we call the minerals baby. Each year a group comes through and puts together a bunch of data and essentially estimates how much material in terms of minerals, metals, and fuels every American born will need in a given year. And as of 2019, each American born will utilize about 3.19 million pounds of minerals, metals, and fuels in their lifetime. So some of these, not that much, 1.5 ounces of gold. I think that's pretty easily accounted for in some jewelry and things like that. But then when you start thinking of other things like over 330,000 pounds of coal, over 20,000 pounds of iron ore, basically every single thing we use in our day-to-day life has a ton of natural resources in it, and they have to come from somewhere. And more and more as we develop more technologies, as we rely on things like Zoom and computers now to even have lectures in classrooms, actually getting to meet this semester, we are also not only just relying on a larger quantity, just baseline of these natural resources, but we're also starting to rely on more and more types of resources. So 50, 70 years ago, the average American wouldn't be carrying around a bunch of rare earth elements in their pocket, but anymore, we all have cell phones, we all have laptops, we all have tablets, we all have, we're going towards hybrid vehicles. And so there really is a push to not only have more of these raw materials, but have more types of these raw materials. And so fundamentally, when it comes down to it, if we're going to sustain the standard of living, if we're going to improve the standard of living, not only with our own country, but globally, we have to be able to supply these resources. And that means finding new sources. And that means actually understanding how they form so we can better explore for them. Because when it comes down to it, most of the really easily found ore deposits that are really obvious and at our surface have probably already been discovered. So we have to get a little bit smarter in how we explore in the future. Okay, sorry, that's my soapbox. I hope you enjoyed it. And sort of when discussing ore deposits, it's always interesting to think of the question of what is rare. So we think of diamonds as rare. Rare earth elements did a really good job of branding themselves as rare. It's right in the name. But what does that actually mean? So I'm sure everyone's familiar, but I'll just go over this just in case. When we talk about the Earth is composed of different geochemical layers, right? And we can kind of simplify that or liken that in a way to thinking about an egg. So the yolk would be the core, the egg white would be the mantle, and then that very, very thin, hard, brittle outer shell would be the crust. And the crust of the Earth is 100% what we spend our time interacting with just throughout our lifetime. And so really the crust is then also entirely where we get all of our different natural resources. And so when we think of the composition of the crust, it's really important to understand that 98% of what we have access to is composed of only 8 common elements. So I've broken that down into this little flashy pie chart here. And so those 8 elements are oxygen, silicon, aluminum, iron, magnesium, sodium, potassium, and calcium. And a lot of these things you might recognize as these are important. We do mine and process a lot of these things. Silicon, if you want glass, you need silicon. Aluminum for airplanes and soda cans. Iron is in basically anything that we build with a structure. So a lot of these things do constitute ore bodies. But when we think back to that mineral baby and we think about everything else that we use in our day-to-day lives, things like copper, lead, zinc, all the rare earth elements, gold, the platinum group elements, everything else, all 84 other naturally occurring elements together comprise 2% of the crust. And that's why fundamentally we need ore deposits, because basically any rock that you pick up on Earth's surface will have some trace amount of basically any element in it. So for example, you know, if you're lucky enough to live out in Jackson and you go for hikes in some beautiful mountains and you pick up the average rock, it will have some copper in it. If you were representing that rock's composition with 1,000,000 marbles, 60 of those marbles would be made of copper, so 60 parts per million. If you're looking at that same run-of-the-mill average rock and you're looking at the gold content, here you'd have to represent the composition of that rock with 1,000,000,000 marbles, and maybe 4 or 5 of them would be gold. So this is why we have to have really specific geologic settings where we've actually concentrated certain metals significantly above these average crustal concentrations, because you simply cannot mine copper or gold or a lot of these things at their average crustal composition. If you were trying to mine gold at 5 parts per billion concentration, you would be moving cities and counties and states to try to get enough gold to be economic. So fundamentally, it's this understanding of abundance and rarity that drives us to need ore deposits to actually concentrate these metals in a way that they are economic and feasible to pull out of the ground. So you pick your element of interest. How do you actually determine where it's going to form an ore deposit? All of this basically comes back to the idea of elemental behavior. And so, you know, we look at our periodic table, and every single element has a suite of physical characteristics and chemical characteristics that dictate how it behaves in Earth's crust. And so this mixture of these physical and chemical characteristics are going to determine, would it rather be in an igneous melt? Would it rather be in molten rock? Or would it be more comfortable forming a solid crystal? Or is it going to be able to travel as a vapor in the right conditions? So basically everything about the behavior of ore deposits comes back to the element you're interested in and how it behaves in a variety of geochemical settings in the Earth's crust. So once you pick your element of interest, then you have to actually think of the other huge suite of geological conditions that are going to affect the formation of an ore deposit. And fundamentally, every single ore deposit needs 3 things. It needs a source of metals, which might be a magma. It could be ocean water. It could be any country rock that happens to be around. You need, then second, a transporting agent to move your metals, which could be, again, a melt. It could be a fluid. It could be that you're really focusing along a fault. And then you need a trap. That's the third major requirement. And essentially the trap is some sort of process or mixture of processes that are then going to force your metals back out of your transporting agent and concentrate them into those really, really higher than average abundances. And so anyone who's familiar with oil probably understands this idea of source, transport, and trap. It's a really basic concept. But when it comes to ore deposits, switching out all your potential different sources or all of your different potential transport agents, and then all of the different things that can act as traps or force the precipitation of the metals, as you interchange these, you basically end up with different ore deposits. And as you change your source versus your transporting agent versus your deposition site, you're going to change what elements are going to be most effectively concentrated as well. So you kind of have to understand, first off, what element am I trying to explore for? And then you can start saying, okay, what sources work best for that element? What transporting agents work best for that element? What sorts of traps do we need to make that metal come out of solution? And then you can start exploring really effectively. And so I guess the big takeaway that I'm hoping people get from this is that I think mining has done kind of a bad job telling the general public how we explore for resources. And The vast majority of people, I think, when you say a gold prospector, immediately think of a guy with a beard and a pickaxe and a donkey, and he's wandering out in the mountains hoping he's going to find something. And that is just not how it works, not effectively anyway. Each one of these sort of elemental metal systems is a predictable geochemical system. And so we know based off of the metal we want, the sources we need, the tectonic settings that form those sources, we know how to better explore because of this sort of equation view of ore deposits. And we're lucky enough to be in a state with absolutely fascinating and fantastic and very unique geology. As I'm sure you're all taking advantage of, Wyoming has just a really fantastic record, geologic record, all the way from, 3-point-something billion-year-old craton all the way through actively depositing mineral formations at Yellowstone. We have so much of the geologic record that is preserved and exposed across the state, and also so many different geologic processes, from ancient continents colliding with one another all the way through active sedimentation and geothermal activity. It really is a fantastic place to get to do geology, and I consider myself very lucky for that. Obviously, we can't delve into the vast majority of the geology of the state here, or even really scratch the surface much on the variety of ore deposits, but I figured it would be fun to pick 3 different places and just talk a little bit about the rocks there, the processes, and of course the ore, because that's what I'm most interested in. And so we'll start off with the oldest, oh, that little circle showed up, the oldest example of ore deposits that we're going to talk about today, which is the South Pass Atlantic City District. And this is clocking in right around 2.6 billion years ago. So South Pass Atlantic City, this is probably the most famous mining district in Wyoming. And I think that comes down to the fact that it is the biggest gold producer in the state. And humans are just absolutely fascinated with gold. Outside of the human aspect of the interest with gold, scientifically gold is really cool too. I already sort of hit on the fact that gold has an extremely low average crustal abundance. Average rock that you pick up, again, sort of 4 or 5 parts per billion, so not a lot of gold in your average rock. And so what that means is to make a gold deposit, we need a very, very high concentration factor. You really need to concentrate gold way higher than background in order to make an economic deposit. What's also fascinating about gold is that it's fairly versatile in terms of the conditions that it needs to travel in a fluid. I'm going to take a brief aside here when I say fluid. So this might be kind of a weird concept. When we're taught geology in undergrad, in our first classes, we always learn there's 3 types of rock: igneous, sedimentary, and metamorphic. And whenever we're dealing with some sort of liquid, it's the idea of molten rock as an igneous magma. What I'm specifically talking about here is not that. What I'm talking about is actually what we refer to as hydrothermal fluids. And in a sense, this is basically then an aqueous dominated liquid, or a liquid with a pretty high water content. And we call it hydrothermal because these are typically heated up in the earth through a variety of different ways. But these are actually pretty common in the upper crust in a variety of different settings. And the compositions change. They might be really, really salty. They could be really reduced. They could be full of hydrocarbons. But it's kind of an odd concept that there's a fair amount of water that can be present traveling through rock pretty deep in the crust, commonly down to sort of the brittle ductile transition at maybe 12 or 15 kilometers. So when I'm saying fluids in these cases, it is kind of an odd concept, but it is sort of an aqueous, you can think of it as sort of an impure heated up water. And again, so gold is versatile in that it will travel in sort of different compositions of these hydrothermal fluids. You kind of have to change the composition a little bit. They can't be perfectly pure water because, you know, if you think about taking a chunk of gold and putting it in a glass of water and setting it on your countertop and walking away, not that much is going to happen. You have to give a little bit of geochemical convincing to get metals to dissolve into aqueous fluids. Some really common ways to do that, you might increase the acidity. If you have a slightly acidic fluid or a very acidic fluid, that tends to dissolve metals much better than something right around neutral. And so two of these sort of modified fluid conditions that gold travels really well in, one is highly oxidized, so lots of free oxygen that's thermodynamically available around at very high temperatures. And then the second really good way for dissolving gold into a fluid is having that fluid be sort of reduced, sort of near neutral, and moderate temperatures. So probably a little tiny bit acidic, but you know, not battery acid. And the reason this second way, this reduced, near neutral, moderate temperature conditions, the reason that this is so important is because it's really commonly formed in a very common major tectonic setting, and that is in subduction zones. So this is probably something that you're all familiar with, but just to refresh folks so I don't go crazy into the rabbit hole without a little bit of background. When we're dealing with all these plates in the crust, so again, coming back to the idea of that thin, brittle eggshell that we live on, all of these plates are moving around, some of them are pulling apart, and importantly, some of them are pushing together, convergent or compressional tectonics. And very commonly what we see throughout the geologic record and active today in some places, will have a very thick continental crust, which is very buoyant, and it will be pushed against a oceanic plate, which tends to be very thin and very dense. And because that oceanic plate is dense and because the continental crust is buoyant, the oceanic plate tends to subduct underneath the continental crust. And a lot of things happen that we won't get into today, but these are crazy active, really important features on the Earth. But for our purpose, they're really important because in that overriding buoyant continental crust, we're creating a lot of compression and we're creating a lot of fluid flow. So as we push these things together and we increase the temperature and increase the pressure, we will metamorphose the rock in that continental crust. And commonly this will drive water out of the rock and then circulate it. So when I talk about the presence of these aqueous fluids, in this case, we have a very easy source for the fluids, which is the metamorphism that's taking place there. And it just so happens that the fluids that you're driving out of the rock in these metamorphic conditions are near neutral, moderately reduced, and at moderate temperatures. So we're creating a huge volume of fluids that are really efficient at scouring gold out of whatever rock they're circulated through. And so basically what happens is we've created this large volume of fluid. It's a really efficient scavenger for gold. It's being circulated through this, metamorphic package as it's being formed in this convergent tectonic setting. It's picking up as much gold as it can because it's very good at it. And then as we continue to form that compression in that overriding continental crust, we're also going to be forming structures like faults and fractures and shear zones. And if you are a fluid and you're being pushed through rock at really high strain rates, at really high compression and you see a fault and a fracture and a shear zone, you bet you're going to shoot towards those openings. They are so much easier to travel through than rock. So basically, all of that really large volume of fluid that has been scavenging gold is now being focused into really, really tight structural areas. And as they travel along, they're going to have all sorts of different things happen to the fluid composition. It might change oxidation state. It might lose its little bit of acidity. It might be oxidized. But basically, we're going to do something to that fluid where we change the chemical composition enough that gold no longer wants to be soluble. And so in those veins and fractures and shear zones, we precipitate out then all these constituents that were dissolved in the fluid, and it forms these large veins or lodes, commonly called, that are quartz rich and have all our gold precipitated out. And this is so efficient, and it's really common. So this is a term that we call orogenic gold. Orogenic means mountain building, essentially, and because we're dealing with these compressional tectonics, we do usually have a mountain building event associated. And so all throughout Earth history, in many different places, we see these orogenic veins and these orogenic gold systems formed where we have similar sort of subduction related settings in the right metamorphic facies. So we've precipitated everything out, and we make these big quartz veins with nice visible gold. And we're in a mountain building event by the name orogenic. And so eventually what will happen is, you know, every mountain chain that's left at surface is going to get eroded down after the mountain building has ended. And you just have wind and rain and weathering, and it's eroding everything down. And eventually those veins get exposed at surface, and they also undergo weathering and erosion. And what's really cool about these orogenic lode veins is they very commonly, as they erode, end up forming placer deposits down in the sediment. So you have these veins with the gold exposed at surface, wind and rain and everything gets to them, and the gold will weather out and be carried downstream by rivers and streams and deposited in the sediments, pretty close usually to the base of the mountain because gold tends to be fairly dense. And so this is actually forming then a separate secondary deposit that we usually call placer gold. And so if you've ever seen Gold Rush or you've ever gone panning for gold, you're basically dealing with a placer deposit, which is gold that's in these unconsolidated sediments that it's been weathered and eroded from somewhere else. And orogenic gold happens to be really, really efficient at forming placer gold deposits. So again, it's a really fascinating way that we can scavenge and concentrate gold. It's always associated with huge tectonic events, and it just so happens that it releases these metamorphic fluids are really the right composition to get that gold and reconcentrate it. And so we see it all over the Earth. So how does that tie to Wyoming? South Pass, Atlantic City District, right around 2.68 billion years ago was undergoing some crustal growth and some terrain accretion. If I'm recalling correctly from Mueller and Frost 2011, the idea there actually is a continental arc is formed, and so this would be sort of along the lines of a subduction zone setting with convergent tectonism. And so it just so happens that it was the right sort of tectonic setting present, and it gets up into the right metamorphic facies of rocks that we would be releasing these wonderful metamorphic fluids to scavenge our gold. What's really cool is that Frost et al. 2006 actually came in and dated minerals from the veins themselves, the shear hosted veins themselves, and got the right sort of 2.6 odd billion-year-old ages as well. So we can tie the mineralization to this tectonic event, and we don't have to wonder if the gold was introduced a billion years later. So this accretion event added the South Pass Greenstone Belt onto Wyoming, a group of sort of metasediments and metavolcanics, sort of metamorphosed up to the amphibolite and green schist facies, and this South Pass Greenstone Belt is the main host for the lode gold deposits, specifically within a formation referred to as the Miner's Delight Formation. Everything here aligns perfectly with what we would expect for an orogenic gold system. The gold is really, really focused in those shears, and the adjacent wall rock, right next to these big structures that would have focused fluid flow very efficiently. The veins themselves are dominated by quartz and carbonate. They have a little bit of alteration associated with them, so sericite, chlorite, and tourmaline. And as is typical for these systems, they have sulfides like pyrrhotite pyrite and arsenopyrite, but these tend to be low total sulfide systems. So they are present, but they're not making up huge volumes, volume percents of the rock. And so when we look at this, the South Pass Atlantic City system, the source of the gold is all of the host rocks, basically. All of these rocks that were being metamorphosed and having these metamorphic hydrothermal fluids flush through them and scavenging as much gold as they possibly could. The transport mechanism is the metamorphic fluids, and then of course the shear zones that focus the fluid flow. But what about the trap? What about the actual reason for the deposition of the gold back out of the solution? Housel 91 suggested that either increasing the fluid's pH, so lowering the acidity, or changing the redox state of that fluid along the shears was probably what forced the gold out of solution. This is really common in ore deposits where there's maybe one or multiple different processes that are forcing metal precipitation. And this makes a lot of sense. So it always comes back to the idea of, what are these specific conditions that you have to meet in a given fluid in order to convince a metal to be soluble? When you go and change later on any of those conditions, you run the risk of making that metal insoluble again. And so in this case, starting off with that near neutral pH, starting off with fairly reduced fluids, made the gold soluble. And if you change one or both of those factors, then it's going to precipitate back out. So a really cool history of the gold formation here and tying to a very, very major tectonic event. In terms of a little bit of the human side, gold was discovered in the South Pass Atlantic City district in 1863, and it was first discovered in placer deposits. That really tends to be the case. And it wasn't until about 4 years later when the actual vein in the sort of hard rock that hadn't been weathered and eroded was discovered, the Carissa lode. And the discovery of the actual hard rock, the source of the gold that created the placers, launched a minor gold rush. And then between 1867 through 1875, basically a bunch of small mines around the area were producing gold. It's always challenging when you have historic production and you have a bunch of small mines and sort of lots of different camps producing. It's challenging to get a really accurate idea of what the production would be, but Housel in 91 estimated that the total gold production out of this area would have been just shy of 350,000 ounces, which definitely puts it at the #1 gold producer in Wyoming. So one of the things that I thought was really fascinating, again, a little bit on the human side of the South Pass Gold Rush, was that in 1868, the Chicago Tribune decided to send a reporter out to Wyoming to document the gold rush. And so the reporter's name was James Chisholm. You can actually get excerpts of most of the journals that he kept on his travels. This is an example. This is just a quick picture of a book that I picked up in a secondhand store, and it's a really fascinating read if you have any interest in mining history or sort of the history of settling the West. But this passage was particularly interesting to me because this is the journalist sort of summarizing the geologic interpretations by the miners at the time. And so not to belabor too much, but I'm just gonna go through this because it's completely interesting. Where the cooling process has been sudden after the great convulsion by which the melted rock containing the precious metals, which is at the base of all other strata, has been forced upward through the vacuum, the gold will naturally fall into masses through the quartz. I would say this doesn't exactly align with how we currently interpret the formation of gold in these systems, but it's fascinating to me because the miners, the prospectors, the geologists of their time, they were trying to subscribe systematic geochemical processes to what they were seeing, and they were trying to do that in order to be more effective explorers. And they were doing that in light of the fact that they had very little science to go off of, and to sort of recall the timing of this. This is what 80-90 years before the wide acceptance of plate tectonics in geology. So really fascinating to see that even at this time, even the prospectors who did have the pick and the donkey, they were trying really hard to see patterns, systematic, scientific patterns in the ore that they were exploiting. This is a little bit more on the human side, but I just couldn't leave these out. The journalist also spent some time in Cheyenne and had some really fascinating thoughts to share. I won't read both of them, I'll just read the second here. When people speak of seeing life out here, I think they must allow a wide latitude in the interpretation of the phrase. So I do get the impression that maybe James wasn't the biggest fan of Cheyenne. He did eventually make it out to, oh, sorry about that. He did eventually make it out to a mining camp at South Pass, referred to as Miner's Delight. And he documented some of the fascinating things going on there, including the capture of a grizzly bear, a young grizzly bear, that was raised as a pet in camp and was later used as food in some slim times. He describes a dinner of buffalo hump as very rough and tough. And I couldn't leave this out, this quote. What a contrast is there between the quiet life of this mountain camp and the roaring hells of railroad towns which I have but recently quitted. Cheyenne, Laramie, Benton, Green River. A sketch of these several places would form an interesting study. So I think it's just fun sometimes to step back and think about the human aspect that's been applied to these. The gold in this system was forming from the collision of plates, massive regional tectonic events. 2.6 billion years ago, the gold wasn't discovered until the 1860s, and then the sort of life and times that were then developed around the camps exploiting that gold. It's just kind of a fascinating prolonged history out there. Of course, today you can go visit South Pass City. It's a state historic park. I believe you can tour the Chisholm Mine and the English Tunnel. So just fascinating to still be able to get out there and be a part of the sort of ever-evolving history of the South Pass district. All right, Newrambler. So we're gonna step a little bit to the southeast of where we started, and we're gonna go a little bit younger in geologic time. I have a question mark on the age here, sort of maybe 1.8 to 1.7 billion years old, not quite sure. And that is one of the things that I think makes the Newrambler system really fascinating, is that there are still a fair amount of open questions with this district. The other thing that makes the Newrambler system fascinating is that it happens to be enriched in platinum group elements. And platinum group elements, they tend to concentrate in ultramafic igneous rocks. So they prefer magmas and melts that are really, really high in magnesium, high in iron. They tend to be heavily sourced from the mantle, very little interaction or contamination with continental crust. You can see some images of what those really high magnesium and iron rocks look like at the bottom here. It tends to give them a very dark appearance. And One of the most famous nearby examples of a really platinum group element rich system is the Stillwater layered mafic intrusion up in Montana, which has just a massive, huge intrusion of really, ultramafic to mafic magmas. So is sort of expected and does concentrate the platinum group elements very effectively. In terms of Newrambler's development, gold was discovered in placers around 1868. So this discovery was right around when the gold rush was starting in South Pass. One of the big differences here, though, is that at Newrambler, there's actually platinum reported from a lot of these placer systems, whereas the placers in South Pass are purely gold. The Newrambler mine opened up shortly before the turn of the century, and platinum group elements were actually discovered in the ores coming out of the Newrambler mine shortly after that. The Newrambler produced sort of intermittently up until 1918, when the Rambler mill and mine buildings were unfortunately destroyed by fire. We do have this sketch from 1905 of what the Newrambler mine buildings would have looked like. In terms of the geology, I already sort of told you a little bit that these are old rocks. Old, of course, in Wyoming can mean an extremely vast range of time periods. But here, the host rocks are sort of 1.8 billion years old, commonly, and some older host rocks as well. And they're dominantly composed of crystalline basement rocks. So schists, gneisses, these metamorphic rocks, granitic and mafic magmas that tend to have some slight amount of metamorphic overprint, and a lot of amphibolite. Amphibolite is a somewhat mafic metamorphic rock that is dominated by amphibole group minerals. And importantly, shear zone tectonism is going to come up here as well. For the Newrambler itself, it's really the only important mine that was developed on a lode deposit in the district. So there were other systems that were developed in or on the veins themselves in the hard rock, but the vast majority of big producers outside of the Newrambler were placer systems. The geology that the Newrambler mine is built on consists of altered metaperoxenite and metagabbro. So I'm going to break this down a little bit. So the meta there simply meaning that there's been some amount of metamorphic overprint on these rocks, but peroxenites and gabbros are ultramafic to mafic igneous rocks. So this is a good sign for us because, as I told you before, platinum group elements really like those ultramafic to mafic igneous rocks. The other thing that's important here is the fact that those rocks have been altered. And what that basically means is we had some sort of hydrothermal fluid come through and chew on those rocks a little bit and change the minerals present and probably change a little bit of their chemistry overall. The third important part of this sentence is that there's shear zones again. And so as I told you before, shear zones are so good at concentrating where fluids are going to prefer to flow, because it's just easier to take advantage of a plane of weakness than to try to percolate through solid rock. And it's in these shear zones at the Newrambler where the quartz veins are developed, and the quartz veins have copper, platinum group elements, and gold enriched. And so this image on the right here from MnDOT, this is a beautiful example of chalcanthite, which is a copper-bearing mineral from the Newrambler mine. So how did this thing form? So the leading hypothesis here, and I'm very open about this being a hypothesis, I would love to see more work done out in this area, is that we had these host rocks, these peroxenites, these metaperoxenites and metagabbros that happen to start off with the right composition. They're ultramafic to mafic, so they probably started off with a high platinum group element component. Then we have this sort of second overprint where we have the hydrothermal fluids come through. They chew on those mafic, ultramafic rocks, they alter them, and they pull all of the platinum group elements out. Then those fluids, very similar to what we talked about previously with South Pass, get focused along those shear zones, along those faults, and precipitate out their metals. So I think one of the neat things here is that we're likely dealing with fairly similar overall conditions between the Newrambler system and the South Pass system. It's not 100% sure yet, we don't know, but it would be a pretty good hypothesis that maybe these are metamorphic hydrothermal fluids that are scavenging the PGEs out of the host rock. Very similarly to South Pass, they're being focused along shear zones and fractures. But the difference here might fundamentally come down to the fact that the host rocks are different. The source of the metals is fundamentally different, whereas in South Pass, you were scouring and scouring and scouring, and you ended up with gold-dominated ores. Here, because you started off with these ultramafic rocks, you're able to end up with ores that have both gold and platinum group elements. So that's the leading hypothesis. It's pretty fascinating. Again, this is sort of driving home the idea that changing one of those three pieces, the source, the transport agent, or the trap, can change your sort of overall ore deposit. I'm going to take a quick detour to lump this into the same system down to Centennial Ridge. And Centennial Ridge, if you've ever driven out to the Snowies from Laramie, you've driven through the adorable town of Centennial, and just off to the south on your left would have been a small ridge, and that's Centennial Ridge. The development history in Centennial Ridge is very similar to the Newrambler district. Gold was first discovered out of placers. A handful of small mines produced gold out of lode deposits out of those veins in the hard rock. Shortly after 1900, platinum and palladium were both reported in the ores, but big difference between Centennial Ridge and Newrambler is that no documented production of PGEs have really been reported. There's a lot of reports that ores went out, that money was made, but assay data is lacking. So kind of fascinating there. But when we look at the geology of Centennial Ridge, it mirrors some similarities to the Newrambler in that the host rocks are very similar. Here we have a lot of amphibolite and mafic intrusive rocks, just like those that are reported from Newrambler. The age of these amphibolites is maybe 1.8 or older, and it's cross-cut by a bunch of shear zones. These are right along the Cheyenne Belt. And so overall, the geology is pretty similar. We have a package of different metamorphic units. We have an abundant presence of amphibolite, and we have the presence of mafic intrusive hosts. And when we actually look at the veins that are also associated with Centennial Ridge, there are a lot of similarities to what's reported from the Newrambler. They are shear hosted. They have a lot of these different textures, some of which are a little bit ductile, some are a little bit brecciated. There tends to be the addition of quartz present. And you know, as of right now, I think it would be interesting to track down some new assay data to try to see what the actual PGE content is of these things or not. But overall, if they are present, it looks like you could probably say a good hypothesis would be something very similar to what happened at Newrambler in terms of having mafic host rocks that are chewed up and altered and probably could have freed up some platinum group element enrichment, and then a large volume of fluid flow that's concentrated into these shear hosted veins. And part of the reason I'm so excited about these two systems is platinum group elements really don't tend to be something that we think of as moving with fluids very much. We think of them as, you know, in these igneous systems, they start off in a melt, they crystallize in the melt, and that's sort of the start and the end of the story. And so having the secondary remobilization of the platinum group elements with a hydrothermal fluid is kind of fascinating, and I think there's a lot of open questions as to, you know, what kinds of compositions do those fluids have to be to convince the platinum group elements to be soluble. Another reason that they're interesting is because platinum group elements were recently listed as critical minerals by the USGS. We have a fairly large import reliance for platinum group elements within the United States. And so even though I have a hard time imagining either of these systems being economic anytime soon, they do serve as really great case studies to better understand how platinum group elements are able to move and be remobilized at Earth's surface. And there's just not that many places in the US that have a concentration of PGEs like this. So a pretty cool area that that hopefully will receive a little bit more academic study sometime soon. All right, the third trip across the state and our last ore system that we'll talk about today is Bear Lodge. I have jumped pretty significantly through geologic time here. The Newrambler Centennial Ridge is maybe a 1.8 billion-year-old system, and now we're going down to 50 to 40 million years ago. So we skipped a big chunk of the geologic time scale. Rare earth elements are probably something that you've all heard a little bit about, or maybe more than you care to hear about recently. They are important, of course, because they're heavily relied upon for a lot of advanced technology. As elements, they tend to be fairly large and very similar in size, so they're sort of outlined at the bottom of the periodic table there in that green box. They tend to be similar in charge as well. And so the fact that they're similar in charge, similar in size, makes it really challenging to process these ores. So we can get the rare earth element enriched rock out of the ground, but actually separating out lanthanum from samarium, from holmium, once we break that rock down and break those minerals down, is a really big challenge, and it tends to be sort of energy intensive and time intensive. So they're fascinating but challenging systems to work in. And when we're usually exploring for rare earth element systems, we tend to think of these being associated with carbonatites or alkaline complexes. And without getting into the nitty-gritty of those definitions, both of these are weird igneous rocks. So with carbonatites, we're dealing with something that has a whole lot of igneous carbonate in it, so things like calcite and siderite and anchorite. And so these are rocks that look like marbles, but were magma and will fizz if you put, HCl on them. Alkaline igneous rocks generally, not always, but generally have very, very low silica. And if you remember sort of back to the pie chart from when I started talking maybe 3 hours ago, silicon is one of the most abundant elements in the crust. So it's very odd to see these igneous rocks with really low silica. And it tends to have really, really high potassium and sodium. So we end up seeing kind of unusual mineral assemblages compared to other things. So the takeaway, rare earth elements, when we typically look for them in ore grade systems, are associated with these weird igneous compositions, carbonatites and alkaline systems. And if we're dealing with a weird igneous composition, it probably has to have a very specific tectonic setting that it forms in. And it just so happens that those weird tectonic settings have been present in the Western United States, sort of here and there throughout Earth's history, but there was a really major alkaline magmatic flare-up in the Western US in sort of the Eocene to Paleocene. And so you can see the maps on the left there from Jensen and Barton 2000. In the upper right, the tertiary, which broadly spans those time periods. A whole lot is going on in the Western US. And so these are interesting because they're not only variably associated with rare earth elements, but also with gold and copper deposits. So as an economic geologist, these things are always really fascinating to see what elements they happen to concentrate. So Bear Lodge in extreme sort of northeastern Wyoming, it's made of a whole lot of sort of smaller igneous phases, lots of different intrusions associated with it. And depending on which one you happen to date, you'll get a range somewhere between 52 and 46 million years old. And this sort of fits comfortably within the larger span of the Black Hills alkaline systems that go anywhere from sort of 58 to 38 MA. But of course, Bear Lodge is best known because of its incredibly weird rocks and its incredibly high rare earth element concentration. So the map on the left here, hopefully you can see the areas that are labeled CH and BH. On the little legend there, that speckly purple pattern is called diatreme. And diatremes are cool. So in these carbonatite magmas, you tend to have a whole lot of volatiles, things like CO2, that want to come out of a magma and be a gas bubble and go off and expand their volume and go out into the atmosphere. So when you're intruding these really, really CO2-rich magmas and they're getting closer and closer to the surface, and those gases want to exsolve out, like when you open up your pop can and it exalts a lot of bubbles out. Basically, it expands the volume incredibly, and it results in these incredibly violent volcanic eruptions, really, really crazy. And so those shallow eruptions, with all their sort of explosive nature, will fracture and break the rock on top of it, and they'll throw it in the air, and you'll mix in the new magma or lava at this point, and you'll create these resulting diatremes, these really explosive volcanic breccias at surface. And the diatremes tend to be heavily mineralized. This is one of the places that we concentrate mineralization in these systems, and they are just amazing looking. And then you can see on the right, so this is a soil sample map from Anderson et al. 2016. You're basically looking at a map of soil samples. So someone went around and sampled on a grid and picked up that soil, and they analyzed the soil samples to see how much yttrium, in this case, which is treated like a rare earth element, is in that soil. And you can see these purples and pinks. These are really, really high yttrium concentrations that are basically telling people, if you want rare earth elements, these are the places within the Bear Lodge alkaline complex that you can explore. And just to give you an idea of what some of these rocks are that I'm talking about, on the left, these obnoxiously large labels D and E, these are samples of carbonatite from Wyoming. Basically, if you put acid on this, it will fizz, because most of this is a mixture of carbonates, calcites, and anchorites. And on the right is an example of some of these diatreme breccias. So these really massive breccias that form from these shallow emplacement of these high volatile magmas that erupt and create these crazy, lava-bearing things. Just as a quick aside, if anyone's heard of Cripple Creek, which is another similar type of system down in Colorado, higher gold, less rare earth elements, it also formed a really massive diatreme complex, and it must have been forested at the time, because miners within these massive diatreme breccias would find chunks of carbonized wood that had been sort of, these trees had been blown up into the air and then fallen back down into the breccia with everything else, and they'd find them, 50, 100 feet below surface. So really, really popping off when these things are being emplaced. So all of that rare earth element enrichment is strongly associated with these weird compositions of magmas that are emplaced into these crazy diatreme complexes. The Bear Lodge system is known for a really diverse rare earth element mineral assemblage that, please don't ask me the specifics about, because I don't even know the names of all those minerals. It's also benefited from some surface reworking that's helped to create sort of a secondary enrichment process. And kind of neat, up in the northern portion of the Bear Lodge system, the system's a little bit more deeply eroded in there. You see a transition from the shallower rare earth element dominated mineralization in the south to deeper copper moly mineralization in the north. So a very cool, very weird system, and really, probably one of the top 5 rare earth element resources within the United States, just here in Wyoming. So that was a whirlwind. Congrats to any of you who could stay with me for all of that. And really, again, to just drive home the point, we're really just barely scratching the surface of what's out there. Wyoming is full of so many different ore deposit styles and types and fascinating places. So I do encourage you, if you're interested, to try to follow up on some of these things. It's been a pleasure to get to start working on these systems and really see the breadth of geology that's just within our little rectangle state. So with that, thanks very much for your time.
I hope we have some more questions. I have a few to start with, and but an incredible overview of the geology that makes Wyoming so special. So one of the questions is about recycling, and how much can recycling make an impact on what we need to produce to support our society, especially in terms of rare earth metals and things like that?
Yeah, what a great question. And so I'm gonna preface this with the fact that I'm not a mineral economist. I don't know all the numbers off the top of my head, but I will say absolutely we should be recycling everything we possibly can. That's just right off the bat. But some of the things that we always have to think about when we think about recycling is, what is the lifetime of use that a given metal goes through? So if you have copper piping in a house, chances are you're probably not going to be able to recycle that for maybe 100 years, 100 plus. A lead battery is a little bit different. Hopefully that'll probably be recycled in maybe 4 years. So there's always sort of an aspect of what is the life cycle of the use of the given metal for the purpose that you're using it for. Yeah, so I can't fully answer that question to a satisfactory degree, but I would say recycling is huge, but it's not fundamentally enough for a lot of the things that we use in huge bulk. So iron, copper, a lot of that we are going through at such a high rate that recycling is wonderful and we should absolutely do it, but it cannot completely offset the requirements to keep building and producing.
Okay. The next question concerns, I think it was your 4th slide where you had a diagram of the tectonic processes, the different subduction zones, and the 2 questions about this really. What is the VHMS, copper, gold, Cu-Au? Could you explain that?
Sure, I can try. So VHMS is volcanogenic hosted massive sulfide. Economic geologists really like their names and their abbreviations. So we give everything a new name and everything a new abbreviation. And so essentially what VHMS or these volcanogenic hosted massive sulfides, these are commonly formed, well, they're always formed on oceanic crust. So that's why you can see, I think the only one little sort of red circle is in the middle of the back arc with a little arrow pointing to it. And formed on ocean floor, these are what we sort of associate with the black smokers. If you've ever seen, a cool National Geographic special where they show the little rover going down and these essentially chimneys on the ocean floor. And what happens here is, for one of a variety of reasons, it could be an intrusive magmatic body nearby, it could be lots of extensional faulting, but you create a circulation of fluids of ocean water. There we go. Basically, it goes down into the ocean crust, and as it gets heated up and as it moves through these typically mafic rocks, it scours a bunch of copper, potentially gold, depending on what the rock is made of, out of it. And then it will eventually hit a turning point where it's gone down far enough, it's cooled back off, it's going to come back up to the surface. And that's where it forms these chimneys. Essentially, as it hits the ocean water, it's dropping temperature really quickly, it's neutralizing, it's oxidizing, you're making all of these chemical changes all at once. And so the sulfur, the copper, the sulfur, the gold, everything will precipitate out as sulfide minerals. And it will form these really, really fine grained, that's why they're called black smokers. It's actually an underground smoke of sulfide mineralization. And those dense sulfides will then settle down into massive blankets, basically of, in a way, sedimentary sulfide. And so they form these stacks, these big piles on the ocean floor of sulfide-rich material that's commonly copper and gold-rich as well.
Excellent, thank you. So could you give us an analog in today's world to the environment at South Pass when the mineralization was happening?
Yeah, great question. So theoretically, anywhere you have a nice subduction zone, the coast of South America, where you have oceanic plates subducting underneath the South American coast, that should theoretically be a great place where this could be actively happening. The caveat there being that it's probably forming 16 to 26 kilometers from the surface. And so we're going to have to wait a while for that to be eroded to be actually accessible.
Okay. Is there a good book about the history and location of mining, metal mining in Wyoming that you're aware of that you can share with us?
Oh my goodness, that is a great question. Oh man, I'm sure someone out there is going to get real mad at me for not knowing this off the top of my head.
No one will get mad at you, I promise.
No one here. Nothing jumps to mind right now, but that is something that I am willing to look into. And if I can think of something, I can email it along.
Okay, that's perfect. The pictures of the rocks you showed from Centennial Ridge look like they were brecciated. Is that in fact correct? Is that a good interpretation?
Yeah, great question. So these vein samples here, these are historic samples that I'm lucky enough to have access to at the university. So I'm trying to actually start doing a little bit of research on. So this one labeled A in the upper left, that's a great example of a breccia. And so you can see in sort of the ugly orangey brown yellow colors on the right side of the sample, they're sort of holding up chunks of the white and green rock. And so that yellow orange stuff would be considered the matrix that's supporting the breccia clasts. And here, because I have done a little bit of work on this, I can tell you this is a really fascinating sample because not only is it brecciated, but it's been extremely altered. So the sort of white and green pieces that compose sort of the left coherent side and the little chunks of rock that are held up in the breccia, the clasts there, those are almost solid albite, which means they're about 7 or 8 weight% pure sodium. And that, I can tell you, is absolutely not how the rock started off. And it's very, very likely that whatever fluids moved through and precipitated out that breccia matrix probably also changed the overall chemistry of the rock as well.
Okay, thank you. We have quite a few questions, so.
Okay, I can try to start. I'm sorry, I tend to get excited and I talk too much, so I can.
These are great. So also, if you could suggest an analog, a current day analog for the shear zone that formed the Newrambler ore deposit.
That one I probably can't do. I am not aware of off the top of my head a good example, but it would be anywhere where there's some really strong compressional tectonism that's overprinting ultramafic or mafic host rocks. But yeah, no good example off the top of my head.
Okay. How supportive is our legislature, the Wyoming legislature, not the federal one, in terms of the need to find and develop ore, commercial ore deposits here in Wyoming?
Yeah, great question. I will say that I haven't really interacted much directly with the legislature, and by much I mean at all. But I have been really lucky to work with a bunch of folks over at the State Survey who are all just absolutely wonderful geologists and very supportive of the work. And I think from both the federal and the state level, there is a big push right now to better understand all critical mineral resources within the US. It's sort of being put at a very high priority. So, I can't speak to money or support in that way, but I can say there is a big push right now. And so I think there's going to be, if there isn't already, there's going to be a lot of support in the near future for better understanding these resources within the US and definitely in Wyoming.
Okay. The diatrimes that you spoke about in one of the last slides, what are the sources of those?
Yeah, so the diatrimes, basically the reason they form is because you have these shallow magma chambers that have just a ton of gas in them. CO2 is the one that's really important here. But you have a shallow, eventually volcanic eruption, which on its own is going to be fairly violent. But then you add in the fact that you have all of these gases that are trying to escape from the magma that really amplify and add to the explosivity of that. And so essentially, these images that we're seeing here, what you're seeing is these big chunks are the rock that was originally laying happily on top of these magmas before they were completely blown up and moved around. And then a lot of the matrix that's supporting them, a lot of that's probably rock flour, just little bits of destroyed rock. Some of it is probably the addition of the lavas themselves that were erupting. And then a lot of times this is where we see the addition of hydrothermal mineralizations. These would be minerals then that were precipitated directly out of a hydrothermal fluid. So these are kind of a garbage bag mixture of things resulting from those really explosive eruptions.
Okay. And the Tetons here locally, lots of metamorphic and even igneous intrusions, but we don't see mineralization, which is why it got to be a national park. Could you comment on why?
Well, there's a lot of options. My understanding is that there probably are a lot of areas that do have good mineralization out in the area, but maybe they weren't as well understood, or when they were first discovered. One of the things that we always have to keep in mind is when we make something a wilderness area, etc., you're basing those decisions off of the economics of the day. So it could be that when people were first exploring, gold was still fixed at $35 an ounce. So, it really changes what's economic. There's also, a lot of fairly young volcanic cover, at least up in the Absarokas. But I would wager a guess that there is a fair amount of mineralization present, and that it's either now completely off limits, so there's really no point for companies to sink money into further exploration, or there's just so much young cover that it's obscured.
Okay. How significant is the current rare earth mining in Wyoming relative to the amount of rare earth minerals that we actually use?
So as of right now, there is no rare earth mining in Wyoming. we have, you know, the Bear Lodge complex, and it's a big system. It's a good rare earth element resource. It is not being developed in any way as of right now. And the most recent production of rare earth elements out of the US in general was out at, oh my gosh, Mountain Pass in California. And it's I would say at this point, and I'm pretty sure Mountain Pass is not currently producing. And so I would say as of right now, the US is importing the vast majority of the rare earth elements that we use, and that it would be a huge addition to what the US is producing if Bear Lodge were to be mined.
And is there any gold mining still going on in Wyoming?
Not at a major scale. There might be artisanal things that I'm unaware of, but there's no major companies that are currently producing. There are some sort of active exploration areas. So there's an active gold exploration project at the Rattlesnake Hills in the Granite Mountains, North Granite Mountains. But as far as I'm aware, there's no current gold production out of Wyoming.
Should the United States be thinking about mining the ocean floor around black smokers to recover those minerals?
Great question. I would leave that up to the environmental folks and the policymakers. You know, the last thing mining needs is another environmental disaster. And so there are a lot of challenges that mining the seafloor. I know it's something that it's starting to be done. There are a lot of challenges that we just, you know, someone like me who's very much on the science side of how did this ore get here and isn't really on the development or processing side hasn't even thought about. I mean, and so I would say it seems like it's going that direction, both for, you know, not so much for black smokers, but for the rare earth element rich manganese nodules. It seems like it's going that direction, but we'll say I hope that if it goes that way, we are extremely careful and think things through before we start making a worse name for ourselves.
Right. So you talked about the carbonites, and they're igneous, but they seem to me to be extremely unusual chemistry for igneous rocks. And could you just talk a little bit about how they are actually formed as igneous rocks?
Yeah, it's a great question, and they are super strange. Again, it happens to be the slide we're on, this D&E panel. You know, when you're an undergrad and you get taught how to identify rocks in the field and you find something that fizzes with acid, you assume it's a sedimentary rock, it's a limestone or a marble, and these things are just absolutely bizarre. And the main setting that we see these things form in is when we have partial melt of the mantle. So we're melting mantle material, which is fundamentally ultramafic in composition. And these things, these carbonatites, because they are also really low in silica, they're also ultramafic in composition. They just don't look like the typical magnesium and iron rich, really dark, you know, mafic, ultramafic rocks we're used to. And so the idea is that you're melting lithospheric mantle, but it's not normal lithospheric mantle. We've done something in its history previously where we've fundamentally changed the composition of that lithospheric mantle. And so we refer to that basically as metasomatized, which fancy word for saying we changed the chemistry. We did something to it where it started off normal subcontinental lithospheric mantle, and it's undergone some sort of process that has fundamentally changed the chemistry. And then you take that and you partially melt it, you know, just melt a little bit. So all of the most incompatible elements, so your rare earth elements, your large ion lithophiles, your potassium, your sodium, whatever happens to be present in that modified mantle is going to rush into this small degree of melt as much as possible. So even though it's coming off of this metasomatized mantle, the composition that we're forming isn't strictly representative of where it's coming from. And so that's basically what we think forms these things, is we're melting parts of the subcontinental lithospheric mantle that have already been altered, have already been changed in their composition. And generally where we see these things, at least in the Western US, we see these things forming after laramide compression has stopped. And depending on who you agree with, either the slab is rolling back or it's tearing off or it's gripping off. But basically after that compression has happened, they say, well, the laramide was weird. It was, you know, flat slab for a fairly long time. It must have interacted with the overlying mantle. It must have metasomatized it. It must have changed the composition. Once that slab goes away, you have a bunch of hot material rushing in and melting that previously messed up metasomatized mantle, and that's what inevitably forms these melts.
Okay.
Yeah,
So,
I hope that was coherent.
yeah, no, it was. So what do you intend your focus to be in the next few years in terms of Wyoming ore evaluation?
Great question. Focus is a hard word. As of right now, I have a student working on an alkaline gold system, a student working on uranium roll front systems, and a student working on some little small copper gold prospects in the Laramies. So I would say that the focus is probably going to be some of these alkaline carbonatite systems, because they represent some really, really fascinating and really truly economically potential systems, but peppering in a whole bunch of weird things just because Wyoming has such a crazy breadth of geology that we can get to. And, you know, from Laramie, a lot of these things are a 40-minute drive from the office. So.
Great. So I want to thank you for an incredible, thorough, and excellent talk. I want to remind our audience that October 6th is our next program. Mike Adler will talk about the geology of Eastern Canada, Northeastern United States, where he's done 20 plus trips by kayak, sailboat, on foot, and there will be wonderful photographs. I also want to remind people that Old Bills is happening very, very soon. Please try and remember the geologists of Jackson Hole, as well as the library. We need your support to continue doing what we're doing. So I want to thank you again, Simone. What a great presentation. I hope we get to have you come to Jackson when we're back in person.
I hope so too. Thanks so much for the opportunity to talk.